Y'all think it's going to snow? Most of my family is around North Georgia and kind of even sort of Athens area. I think it's supposed to snow there first. And they might be snowed in for a few days. I kind of wish I was up That's what people want to see. So I will upload this PowerPoint. So let me just kind of do a review of what we talked about. And then I'll go into a little new stuff, and I'll try to go over a bunch of problems today. Types of things you can solve. I don't have anything in D2L yet. Hopefully I can get that together, but I'll show you the types of problems you'll need to solve up to where we are. Okay, intermolecular forces. So the main thing is these three intermolecular forces. The dispersion forces, the dipole-dipole, the hydrogen bonding. Dispersion is the one that's instantaneous dipoles. All molecules have those. It's sort of like the cloud of electrons can deform. The easier it can be deformed, the more polarizable we call it. If one of them gets knocked out of whack and it gets a negative or a positive, then another molecule will see that negative and it will push the negative cloud away from it, and then that side becomes a little positive. So these usually just come from fluctuations of molecules banging into each other. So the larger a molecule is, your book likes to say higher molecular weight. I think it's better to say how big the molecule is, or at least how big the electron cloud is. Makes them more polarizable. Here, I'm going to upload this. I just want this to keep up with what I'm saying. Right, so dispersion forces. The dispersion forces are sometimes referred to as instantaneous dipoles. What you know of as polarity is the same thing as dipoles, and those are permanent dipoles. So it literally sits there as a positive and negative, and it doesn't go back to neutral and then get deformed. So those we call permanent dipoles. So the dipoles you know about, the polarity of molecules, polarity of bonds, polarity of molecules, those are the permanent dipoles. So the dipole-dipole interaction is the next strongest. Then there's hydrogen bonding that literally only comes from hydrogen bonded to fluorine, hydrogen bonded to oxygen, and hydrogen bonded to nitrogen. Those are the strongest intermolecular attractions you can get. On this list, this is, I guess, the third slide where it says bulk properties of liquids. We've talked about those first two in the left over there, boiling points and melting points. So there's a good list of properties that liquids have. And I suppose melting points is related to a liquid, but all these other ones are related to liquids. I'll talk about vapor pressure today. You ever heard of viscosity? Do you know what it means? It's sort of like if you've got a liquid here and another liquid here, and you stick down in it and you try to push your way through it. Or you can also picture that this room is full of the liquid up to here, and I try to walk. You ever try to walk in like ankle deep water, or no, knee deep water? It's kind of hard to move your legs. The harder it is to move your legs, the higher the viscosity. It's just how easily does it flow. Cohesive forces, or are what we refer to as, it's kind of what we've been talking about. the forces among the molecules in a bulk sample. We've got a bunch of the same type of molecules. Cohesive is how much are they attracted to each other. Adhesive is how much are they attracted to another thing. Like you could picture a water droplet sitting on a branch. That's adhesive forces between the water and the branch. Surface tension, same idea. You've ever heard of surface tension? You have, haven't you? So down in the bulk of the water, every water molecule is being sort of pulled in every direction equally. But once you get to the surface, it's only being pulled downward and maybe to the side a little bit. There's nothing pulling it up. So the surface just kind of gets a little tight like that. So that's the surface tension. What else is there? Capillary, usually called capillary action. Heard of this? It's just the idea that a liquid can wick its way up onto something. That's related to adhesive forces. The whole point is everything on that list. You could say it this way. Well, you know what boiling temperature is. The higher the strength of the attractions, the higher the boiling temperature will be, because you've got to put more energy in there to get the molecules to come apart. But all of these are the same way. The first two on there, the unit is temperature, boiling points and melting points. Vapor pressure, that's just measured in the units you've heard of as pressure that was introduced last semester. All of these others have other odd units that go with them. But for that whole list, picture a unit, like for the first two it's temperature, for the pressure when it's kilopascals or atmospheres. All of those have their units that go with them. And of course, all of them have their units to go with them, and they all have a numerical value that denotes them. And what I'm getting at there is, regardless of unit, the stronger the attractions, the higher that number will be for all of those. So it's that simple. I'll go into vapor pressure a little bit. I might go into viscosity a little bit, but the general idea is, if you're looking at something and it says the viscosity is this, and it's got some weird units, and then you say, now here's another molecule, does it have higher or lower viscosity than this one? You do it the same way you would do higher boiling points or lower boiling points. Whichever one has the stronger attractions, that's going to be the higher number that goes with the units for whatever one of these properties we're talking about. Okay, vapor pressure. So you see this graph of number of molecules versus kinetic energy. Here's something that I'm sure you've seen somewhere. It's called the normal curve. So if you had a graph of something, so you've seen this in statistics or something somewhere, right? That isn't the only statistical curve that exists. There's a good handful of them for various things. Those curves that you see on there that are shaped more like kind of go up, and then they have a long tail that goes out this way. The name of the curve is slipping my mind, but it's a different type of statistical curve. But this is actually the curve that kinetic energy will take. Number of molecules for the normal curve, my ugly normal curve. What this really represents is whatever's on this axis. It's saying anything that from here below, this is that sort of like the area. The area here represents how many things have a score along here below that. And this would say the area here tells you how many of these things have a score from here and below. So if you have kinetic energy, I guess I should go back over here. If you're looking at this kinetic energy, basically what happens, this is low temp, and at higher temperature it gets a little flatter and a little longer. And what you see on there is that dotted line that says, let's say that's how much kinetic energy you need to escape the liquid. So if you have this lower temperature, There are a few down here. What if I shaded it? That's even probably too much, but what I'm getting at is even at room temperature, you've got this distribution of kinetic energies of the particles in the liquid. And there are a few of those particles that have enough kinetic energy to escape the liquid. And that's I said room temperature, but let's say somewhere between melting point and boiling point, somewhere in there. There are some that have enough kinetic energy to leave the bulk. Let me fix this a little bit so it'll match your intuition a little better. Let's make the dotted line here. Shading in this little part here. And we make this one its higher temperature. Make it a little flatter. A little longer. All right, so there's this area for the low temperature. And then there's this bigger area, including this, for the higher temperature. And the point is, you know what would happen if you took, say, a beaker of water and we set it on this desk over here, and it stayed at room temperature. That's above its freezing point, and it's below its vaporization point. But if we left it there, I don't know, a few days, what happens? You do know this. It's something you already know. Let's say we let it sit there for a year. When we come back in a year, what are we going to see? You do know this. Huh? It evaporates, right? A glass of water is not going to sit there forever. It eventually evaporates, right? You get wet in the rain, you come inside, you stand around a little bit, eventually it evaporates. That's what this represents. Tiny amounts of that water is actually escaping into the room if we just have a beaker shape over here. See what I'm saying? If we raise the temperature a little bit, it'll evaporate a little faster. If we leave a beaker sitting here, it says 100 milliliters, and it's 20 degrees right now, we come back and it'll go down some. But if this room weren't 20 degrees, let's say it was 50 degrees, no, it's not saying that, it's too hot. Let's say, well, whatever, let's say it's 40 degrees, then more of it will have evaporated in a day than otherwise. And this is the warmer temperature, so you can see that even more of them are escaping per unit time, per amount of time, or whatever. So that's evaporation. All right. So that kinetic energy curve, it's kind of non-intuitive, but if you look at it, think about it a little bit, you'll see what I mean. That little bit that's crossing the line for the low temperature is representing evaporation, and this higher temperature, that's kind of representing evaporation too. And you have to ask yourself, what does this curve look like when you actually get to the boiling temperature where everything boils very quickly? And really, it's just a very flat curve with lots of area over here on this side. You still have some over here. It's always anchored over here. But that's sort of kinetic here. Let me show you. Let me skip this. I should have done this. So I made this little graph. So where you see vapor pressure, and you see slide number 8. I forgot which one of these. One of these takes me back to this. It's control. So look at the scale on the far left there. What slide did I say that? Slide 8. So I've got the temperature scale over there, and the two dots represent the freezing point and the boiling point. So let's say we're somewhere in the liquid range where the arrow is pointing. So you have evaporation going on, and the vapor pressure, if you picture just above the surface of the liquid, sort of want to go over there and point, but I've got a video going. But just above the surface of the liquid, those bits of escaping particles, if you put a plane up above there and you measure the pressure that those put on it, they do actually have a pressure that you can calculate. You can measure it too, but it actually exists. I've got indicated on there, let's say the vapor pressure is 0.5 atmospheres. Normal atmospheric pressure is 1 atmosphere. So you've got 1 atmosphere of pressure going down on the surface of the liquid. And I'm probably exaggerating there, but the 0.5 is saying that you've got if you put a plane just above the surface of the liquid and measure the particles hitting it, that pressure would be 0.5. You raise the temperature a little bit. Now the vapor pressure is 0.8, literally because you raise the temperature a little bit, more particles are escaping. More particles have this range of kinetic energy. So you have more particles escaping. You follow that? All right. Okay, even closer, even more particles are escaping. I had fun making this diagram. All right, and then you get to a point. Oh, I should have said, look at the progression. So we have 0.5 atmospheres. The next slide shows more escaping at 0.8 atmospheres. 0.95 atmospheres, we're getting very close to the atmospheric pressure. When you hit the atmospheric pressure, that's when it boils. So if it was water, that's when it starts going bubble, 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 and it all just goes away very quickly. That's because this gets so flat and so many things are out here that they just start escaping very easily. If you ask yourself, what happens to the ones below here? That's kind of kinetic, some kinetic theory that I'll save that to talk about it when we get to equilibrium. But even if there's some particles that say have this kinetic energy, they're constantly banging into each other and getting faster and slower, and just, one particle doesn't keep the same kinetic energy it keeps. So all of these particles that are down here eventually make it to higher kinetic energies and leave. It's just it all happens very fast once you get to the boiling temperature. So the boiling temperature, also known as the normal boiling temperature, is the temperature at which the liquid boils. Or no, it's the temperature at which the vapor pressure equals the atmospheric pressure. That's the boiling point, also known as the normal boiling point. This is also a view, the next slide on phase transitions. Notice the ranges I have there on the right. Those aren't really phase transitions. On the left, I have the phase transitions marked with arrows. On the left, I have them marked with arrows. And I just want to point out, right there in the middle, liquid, last semester, we used specific heats. That was in joules per gram per degree C. And that had to do with changing the temperature of the liquid. At the bottom, the solid, we did do that a little bit, specific heats of metals. We did a lab on that in here. We put metals down in water and a styrofoam. No, we actually had decent calorimeters. But then we figured out what is the specific heat of the metal. We probably didn't talk about temperature changing of a gas up there at the top. But it's the exact same idea. How much energy does it take to raise 1 gram of whatever, steam, whatever you've got vaporized, 1 degree C. On the left, you see what we're talking about now, these phase transitions. And just notice, it's joules per gram, not joules per gram per degree C, because the temperature doesn't change as you add energy to it. So at the very bottom there, you're at a very low temperature, it's a solid. You add a little bit of kinetic energy, that is, you raise the temperature, you start to vibrate, they vibrate more and more. You keep adding energy, that is, raise the temperature, that is, increase the kinetic energy. Once you get to the phase transition point, you're still adding energy, but the energy is now getting them to overcome their attractions to each other. It's not raising the temperature. It's not increasing their kinetic energy. It's getting them to come apart. And once they all come apart into a liquid, then next little drop of heat you put in there to raise the temperature, next little bit of heat, yes, energy you put in there, now it goes into raising the kinetic energy. So they move faster and faster as the temperature goes up across the liquid. Then when you get to the vaporization point, you keep adding heat That is, you keep adding, you're not increasing their kinetic energy though. You're overcoming their attractions to each other, and then they escape as a gas. And then from there, you can continue to raise the kinetic energy of the particles. That is, raise the temperature of the gas. But the phase transition, there's no temperature change. I don't think I mentioned, this is kind of a busy slide, but the next one just reminds you that when heat is going in, it's an endothermic process, and when heat is coming out, it's exothermic. I just put that there. If you're raising the temperature of a solid, that's an endothermic process. And then we get to that transition point between solid and liquid. You're putting energy in, so the phase transition from solid to liquid, that's an endothermic process. It's not a chemical process, it's a physical process. But then when you get to everything's a liquid, putting temperature in to raise the temperature, endothermic. So all the way up into the vapor phase. But if you start cooling it down, that's exothermic. And then you get to the phase transition between vapor and liquid, and you're still removing energy, so it's still exothermic. So going from vapor to liquid, that's still an exothermic process. Exothermic, yeah. So it's exothermic going down and endothermic going up. I didn't mention this the other day. It is possible to go straight from a solid to a gas under certain conditions. I won't say much more about that, but there is such thing as a similar to specific heats, similar of heats of transition. There is a heat of sublimation, and going the other direction is deposition, going from a gas to a solid. And I put these in there. You'll probably want them as a reference for solving problems. So the next slide has heats of vaporization of several different substances. And notice at the top of each chart, you see joules per gram. So the number you see, the units, is joules per gram. Heats of fusion, same thing, joules per gram. And I just noted on here, this slide doesn't have to do with phase transitions. This is literally a chart that I used last semester. And this is just specific heats for raising the temperature or lowering the temperature. So it's in joules per gram per degree C. You with me? So that's kind of a throwback to last semester. All right. Okay, problems to be able to solve the test. This is example 10. 10.7, chapter 10 on OpenStax. I will go to the book on the screen. So if you're stuck watching the video, you'll want to go to that in chapter 10. Let's see what's on the screen. But I'm going to look just above there. Estimating enthalpy of vaporization. And you go up to where you see So just below example 10.6, you see the Clausius-Clapeyron equation. That form of the equation, okay, fine, but that's not the one we typically use. Rearranged a bit, you can get it to look at the next one down that says natural log of pressure. And then you play a few more games. Let me skip on down here where you've got natural log of pressure plus the delta H of vaporization is what this means, delta H of vap. And then you mess with it a little more, you get to the one that's just above 10.7. And I will start there. I didn't even tell you anything. Just kind of as an aside, heat of vaporization, enthalpy of vaporization. Yeah, That's what they call it here. Delta H. Okay. And those are all synonyms. That's all I wanted to say. And same for the fusion. Heat of fusion, enthalpy of fusion, delta H, FUS. Those are all synonyms. You could use any one of those to refer to this. Enthalpy is just sort of a fancy name for energy in thermodynamics. So they're calling this enthalpy here. So I wanted to write so I could call this the Clausius-Clapeyron equation, but really it's a slightly different form. Natural log. I won't tell you where this comes from. It's pretty complicated. You would have to take a advanced thermodynamics class to see where this equation comes from. H vaporization. R is the gas constant. In this case, we're using R equals 4. What is it? Kilopascals. Meter mole Kelvin. They never put the units there. There's kind of a difficult description of how the units work for this, but I'm going to just leave that aside for now. 1 over T1, 1 over T2. I'm happy to give you this equation rather than have you memorize it. But this problem I'm about to show you, you're given a T1 and a P1, a T2 and a P2. I'll give you R as well. But I'm kind of going to ignore the units here in a way. But watch how I do this. The first thing you want to do, if you're given a P1, a P2, a P1, a T2, that's these. I'll give you R. And if you have those things, you can find, it's really kind of an estimate, but it's a very good estimate in most cases of delta H vaporization. But first what we need to do is solve for delta H vaporization. What I would do is divide both sides by 1 over T1 minus 1 over T2. So that's that. And then you multiply both sides by R, and that gives you R times natural log of P2, P1. Does not look like a delta. Anyway, this is the equation we want to use. And from here, it really is just plug and chug, but I'll take you through it. So we're going to use R times natural log P2 over P1. So this delta H of vaporization that we're calculating, that's literally, I'll go back to my slide. I'm trying to estimate this number. This example is doing isooctane. read the problem it's telling you to do isooctane.
For the temperature, do we have to convert it?
Yeah, I was about to get there. All right, so we're using that equation, and we're given as values of this. This is what you would be given if you're solving one of these. At different temperatures, you have a different vapor pressure, and then at the boiling temperature, the vapor pressure equals the atmospheric pressure. So these pressures are vapor pressures. And this is P vapor 2, I'll call it. All right, so what we're given for temperatures and vapor pressure 1 is 10 kilopascals for pressure, and then 98.8 degrees C. But yes, we have to convert the temperature to Kelvin. So 34.0 plus 273.15 equals, can you do that in your head? Either can I. 273.15 307.15. Truthfully, this is addition, subtraction, 1 after the decimal, 2 after the decimal. So I really need to round those back to 1 after the decimal. So I'm going to use 307.2 K. And then this one, 98.8 plus degree C. Plus 98.8, 371.95. So 371.95, but really we have to round it to 372.0. Okay. So those are what I'm going to plug in for temperature here. And like I said, the units here is kind of a long walk. I may go into it on another day, but I'm just going to show you how to plug and chug here. I'll just say here, you end in joules per mole. And yeah, the units do crunch to that, but you have to describe newtons and newton meters and things like that. So I'm not going to that. All right. So using this equation, R is 8.314. I want to multiply that by natural log of T2, vapor pressure 2, and I'm going to skip the units now. Over vapor pressure 1, which is 10.0, and then 1 over T1, over T2. That will give us vapor pressure. What was I going to say? Oh, they gave us these as a pair. They didn't call them T1 and P1. They just said at 34 degrees C, isooctane has a vapor pressure of this. At 98.8, isooctane has a vapor pressure of this. So you do pair them based on the way they're presented. But I chose to call these 1 and I chose to call these 2. It really doesn't matter which way you do it. If I had called these 1 and these 2 and plug them in the opposite way, meaning I would have these 2 swapped and these 2 swapped, it comes out exactly the same. So it really doesn't matter which one you call the 1s and which one you call the 2s. All right. You know how to do log in a calculator? 100 divided by 10, which is of course 10. I have to go to my scientific, and I've got to find the ln. In this, so you do that division first and you get 10, and then you find the natural log of that at the 10, and I get 2.3. Um, 10. So if we did this division, we would have 3 significant figures. And the rule is when you're doing log, I think you start at the decimal, and those are the 3 you're keeping. But when you do a log, it's a little weird when it comes to round off error, so I always keep 1 extra. So make sure you keep, so if this is 3 significant figures, after you do the log, you want to keep 3 after the decimal, no matter what's here. I usually keep an extra, just probably tend to come out better. Significant figures with logs and with logs is weird. You notice we don't cover that beginning of the semester, last semester. And let's do these divisions. 1 divided by 307.2. That's going to be 4 significant figures, so 155 minus 4 significant figures here. The 1 is infinitely precise. 1 divided by 372.0. 0.002688. So again, this is just plug and chug. So the numerator, I'll do the numerator by itself. 8.314 times 2.0. No, go back. 2.3025. Yes, I'll keep 4 significant figures. And then the denominator, 0.00355 minus 0.00268. And then to finish it out, 19.14 divided by 0.00862. Well, when I did this yesterday, I got the right answer. I must have punched something in wrong. Should be 33 something. Do you guys see me do anything wrong?
I think it's the denominator. I got 0.000567 instead of that.
I did something wrong. 0.003255 minus 0.02688.567. Is that what you got? $19.14 divided by 0.000 567. All right, so we get, this is what my calculator says. We'll keep 4 significant figures. Yes, do they keep 4? 3, 4, oh yeah. 2, 3, 8, yeah. Those are, they kept 3. Oh yeah, these should have been 3. Right? I think they did it wrong. Anyway, it's okay. We'll keep 3, which gives, just so it matches the book. 5 rounds to 7, so it's 3 through 8, and then these 2 are zeros. And there's the decimal, but I don't want to put the decimal there because that indicates these zeros are significant. So I'm going to do that. So after all that crunching, that's the number we come down to. The one we had in there. 33.8. Yeah. Okay. Like I said, I skipped a unit analysis here because there's this thing between kilopascals and newton meters and the R value. But for a problem like this, just realize it comes out in joules per mole if you do it the way we just did it. Okay. Check. The one I'm going to have you do at home uses kilopascals as well, so it'll be exactly the same. So you could, so that's the answer, or you could go 33.8 kilojoules per mole. So you move the decimal 1, 2, 3. Maybe that's a better representation. All right. So let me write this. What we've just figured out is the delta H equals, I'm going to use 33.800. So for my purposes, what I'm about to do, that's the one I'd rather keep. That's what we just found out. The delta H evaporization is the same thing as the enthalpy of vaporization, and it's the same thing as heat of vaporization. I have a list of all these heats of vaporizations here, but these are in joules per gram, not joules per mole. Joules per gram. What about joules per gram? All right. To find the joules per gram for isooctane, I gave you a picture of isooctane here. Slide. Problems to be prepared for on the test. So that was example 10.7. I've got isooctane there. 8 for octane H. How many hydrogens are there? That's probably not the best representation, but you can still kind of see it. So that's isooctane. How many hydrogens are there? How many? 18. So that would be the formula for this isooctane. Molecular weight is for H, we've got 18 of them. 1.01 is the number on the periodic table for the molar mass. Carbons, we have 8 of them. Periodic table would tell you 12.01. So if you multiply those up, 8.18 and 8 times 12.01. This should be a review. that right? Isooctane 18. I don't know why that seems wrong to me. 8 times 12.01, 96.08. Okay, I guess that's right. So that would say gram per mole. So that looks familiar, right? You remember doing that last semester?
Is the hydrogen supposed to be 18?
Yes. That's what's wrong. Something was wrong. That's the one I did in my head. See? That's why I didn't do them in my head in front of class. 8 times 1.01 is indeed. Oh, that's what I did. I did 8 times 1.01. 18.18, all right, plus 96.08. All right, so what we actually have is 114.26. Okay, that feels better. So what I'm going to do is get this from joules per mole to joules per gram using this. Get all this out. You guys ever study friction anywhere? Come up in high school stuff. I'm teaching that in another class right now. Brand new ones of these creates a lot of friction and it wears me out. It's very simple. All right, so here's what you do. We've got, I'll tell you guys, for those who haven't taken me before, whenever you have units written like this is really how you write the units in text. You write a paragraph and you write this, you go joule/mole. When you're about to do math, what I like to tell people is, this means whatever the number is here, it goes with this unit on top. And just a 1, an infinitely precise 1 goes here, meaning joules is 1 mole. 1 mole. That's the way I like, the form I like to have it in if I'm going to do math with it. So just so you don't get lost when I do this. It's kind of like miles per hour. Right? That means I went 55 miles in 1 hour. That means I went 55 miles in 1 hour. That's the form I like to have it to do math with. Okay. So I've got this. 800 joules to 1 mole. All right, now I'm going to use this, and again, I would tell you to do this, 114.26 grams to 1 mole. So I've turned that into the way I like to use it for that. Over here you can see that we need moles on top to get the moles to go away. So I'm going to flip that over. 1 mole is 114.26 grams. Now the moles cancel and I'll end up in joules per gram, which was what I was trying to do here. The rest is just do the math, which in this case is division. So really, ultimately, this is just dividing 33 divided by 15.26. I get, so I'm going to do 3 significant figures. There's no way that's 33800. Divided by 114.26. Yeah. I don't know what I put in the first time. So this is 3 significant figures. This is 5, so I'm keeping 3. So we're really what I want to do here is 296. It's joules per gram. So I should be able to look on my chart that has these in joules per gram, find isooctane, and it should be something very close to this. It doesn't happen to be on that chart. What I'll do is kilojoules per mole. Well, I looked this up earlier and it popped right up. That's not isooctane. Well, ever since they started using AI for searches, it's been terrible. So I just want to show you that it comes out very close. Kilojoules per mole. Joules per mole. Well, when I looked this up yesterday, it popped right up. And I think it said 300 joules per mole. But today, whatever AI is running this, whatever, take my word for it. What's listed in most of the tables is 300, so we're very close. All right. I did put on the slide try to check your learning part of 10.7. So if we go back here, just check your learning. So now they're talking, it's the same problem, but now they're saying ethanol. And on my slide, I gave you ethanol. That's ethanol. So it gives you the structure so you can use the chemical formula to calculate the grams per mole. And ethanol is on this chart. I'll upload this PowerPoint. Ethanol is on there, I think. I can't see it. Do you see it? I swear it was there yesterday. See it? There's kilojoules per gram, but that would mean 826 joules per gram. So hopefully you can search it and check your answer later. But try that one just so you have one to try on your own. Try, go to example 10.7 and do the check your learning one. Oh, they give you the answer. Oh, so that's what you should get for joules per mole or kilojoules per mole. But I've asked you to go one more step and find the joules per gram the way I did here. So be able to do those things. That's something that you can practice, though. Okay? All right. Another thing I want to do today is to do okay. These are the ones that we can practice. Exercises 13, 15, 11, 13, 15. Maybe I didn't mean it. 17, and it's related to 48. So look at that when we get to it. 21, 31, 35, 29. I guess I just didn't put these in order. 29, 31, 35, 29, 31, 35, 41, 45, 51, 38. So as far as practicing something for the test, these are the types of problems. There's this one, exercise 10.7, and then there's these in the exercises. I hope to get a bunch of these on D2L so you can practice soon. Certainly by the time the test is getting close, I'll have all those up there that you can practice. But for now, let's go over these. Exercise at the end of chapter 10, number 11. Oh yeah, we went over that the other day. Can you tell, looking at 11, this is just a review, but looking at number 11A, which one's going to have the highest boiling point? HCl, H2O, or SiH4? Remember this? Anybody? Which one has the highest boiling point? What is it? Did you say water? Yeah. There's 2 hydrogen bondings for each water molecule because it's an OH bond. Let me move forward. If there's time, I'll come back and review that one. For this one, you need to know the structure, and I will give you structures. N-butane is, so look at this structure. Versus, it's chloropropane, chloroethane. Cl. That's chloroethane. These are chosen the way they were because they're very close in molecular weight. What's the question? Which one has the higher boiling point? Explain the differences. Okay, it's telling you it's -1. So just below 0 degrees C, that will evaporate. Not evaporate, boil. And the other one is 12 degrees C. So these are boiling temperatures. What else? So 20 degrees C is probably about what it is in here right now, maybe 18 because it's cold. So why is there this difference? Why is this one lower than this one? How would you describe it? So what are the intermolecular forces? Dispersion, dipole, and H bond. Weakest, in the middle, strongest. Do you see any H bonding anywhere? No. For there to be H bonding, you need H to F, H to O, or H to N. And none of those are there, so we can ignore that. Dispersion forces. Do these have dispersion forces? All molecules have dispersion forces. I think size-wise, these might have been chosen based on size, but chlorine is a good bit bigger than everything in the row above it. So it's a good bit bigger, so probably size-wise, these are probably comparable, because chlorine would be real big. But what's the other difference? So I'm saying they're probably the same on dispersion, roughly the same size. But one of them would definitely stick to itself, not to itself, but another one of itself, a lot stronger than the other one. Why would that be? Dipole. If you pull out the periodic table I gave you last time, and look in the bottom right corner for chlorine and carbon, you'll find that this is polar. So you would have a dipole here. Like that. Slightly negative, slightly positive. So that's the way you would rationalize it. You have a bulk bunch of these. They stick to each other more strongly than these will stick to each other. So this one boils at the lower, higher, boiling point, that one boils at higher point. You with me? I try to do everything multiple choice. This chapter is making it very challenging to do that. But I might say, what is the main difference? What's the main thing that explains this difference in boiling point? It's going to be A, dispersion forces, B, dipole, C, H bonding, D, some bullshit like density or something. And then the answer would be the dipole. They're probably the same on dispersion. Hydrogen bonding has nothing to do with it because neither of them have that. The only difference it could be is the dipole. You with me? That's 13. All right. The melting point of H2O is 0 degrees C. This is 15. So here's three choices for what it might be for H2S. H2O. Let's see here. A little cheat note there about intermolecular forces. Zero degrees C. 0 degrees C. All right, and then for the other one is H2S. All right, and it gives you choices for H2S. Negative 185, negative 133, negative 85. Oh, look at the wrong one all of a sudden. It gives you negative 85, 0, or 185. All right. And A, B, C. If one of those is the actual melting point of these, which one do you think it would be? A. It would be A. These have hydrogen bondings. This does not. They both have dispersion. S to H, I can't remember if that's polar or not. But the point is, these are going to stick to these so strongly because of the H bonding. And this doesn't have H bonding. This one is necessarily going to be lower than water. And this one means it's the same as water, 0 degrees C. This would be higher than water. That would be sticking to each other more strongly than water. Definitely they stick to each other more weakly than water. So it has to be this one. You with me? Everybody good with that? Everybody take a sip of their drink. And next, 17. Okay. I have told you that's the strongest among the hydrogen bond. Next in lines, those are the next strongest. H at the end is the weakest of these very strong ones. we're comparing water HF, and which property did I mention here? 17. They don't mention it properly, they just say, why is hydrogen bonding between two molecules, two water molecules, is weaker than hydrogen bonding between the two hydrogen fluoride molecules? Skip that one. It's making me parse too much. I thought it was going to be weaker. Okay, the answer here is going to be the polarity of the molecule, but that's not. Yeah, okay, skip that one. 21. There is a chapter on organic chemistry. I didn't really cover, well, let me say this. Do you remember, so you get a formula for something. This is kind of an aside here. You're given a formula. My phone got one of those updates the other day, and it's really struggling with me. So all of you, did you study this last semester where that's a structural formula? C2H6O, and that's the chemical formula. So there's one oxygen, there's 6 hydrogens, and 2 carbons. So that's the molecular formula. That's a structural formula. Did y'all do structural formulas? You did last semester? Well, if you were in my class, you did. It comes up more in this class. Raise your hand if you did structural formulas. Any more? Okay, good. Most of you need this description anyway. This kind of gives you a hint of what the structure is. So the least amount of information here, a little more information here. The information you really want is literally the structure. What you wish you had instead of this. OH. We very frequently, for OH, we don't draw this line because it's such a common constituent. So I'm just going to say OH, but there really should be a line. What you wish you had is that instead of that. But this just says, going from left to right, this carbon is a CH3. This carbon is a CH2 with an OH on it. And that's really what you need. You really need that structure to look at to answer this type of problem. So I'll tend to give you that instead of that on a test or on practice tests.
First, you're going to give us like the diagram?
Yeah, I'd be more tempted to give you this rather than make you figure this out. There is a chapter where we go over this, but since we're doing intermolecular forces, I'd rather just stick to one thing. So this was A. B is CH3, CH2, CH3. So the way you unravel that into, what I'd probably give you instead of that is CH3, CH2, CH3. So that's the structure of B. This one would be did I do this one the other day? For some reason I feel like I did, but whatever. So really comparing these, I think the question is just what IMFs are present. What IMF do all of them have? Dispersion. So they all have dispersion. Which ones of them have hydrogen on? A, is that all? Yes, that's all. The only one that has any of, I erased it. There's your hydrogen bonding, and there's no other hydrogen bonding covalent bonds there. So they all have dispersion. This one has dispersion and hydrogen bonding. Okay, which of these have, the only thing left is dipoles. Which of these have dipoles? C does, but really this one does too. In some sense, this is just a very strong dipole, but there's actually a dipole here too, between the carbon and the oxygen. So maybe that's a little tricky, but this one has dispersion, dipole, and hydrogen bonding. This has only dispersion. This has dispersion and dipole. Which one has the lowest boiling point? E for sure, because it only has the weak dispersion. Which one has the highest? A, because if I said Y, A, B, C, D, you would say it's because of the hydrogen bond. That's why it has such a high volume. Maybe I would phrase it better than that. 21. No, definitely not. I haven't gone over that either. Forget that. Okay, I'm glad I didn't help you on this yet. Oh, I meant to say 39, didn't I? Yeah, I meant to say 39. 29 shouldn't have even been on the list. Okay, so now I wanted to do 31. Which one was 21? So we go from 21 to 35. Yes. Lost my mind here. Sure my list there is written correctly. Where was I? 31. 21. Okay, good. All right, 31. Heat is added to ice at 0 degrees C. Explain why the temperature of the ice does not change. What does change? You've got ice at 0 degrees and you start adding energy to it. You start adding heat to it. But the temperature doesn't change. What is changing?
It's a phase change.
It is a phase change. That's one way to put it. The molecules are getting a little further away from each other. Solid ice, you keep adding, they jiggle more and more, and then you get to the transition point, and the energy is overcoming their attraction still, so they can swim around each other. That's what's changing. The distance, another way to say it is the distance between the molecules. 31, 35. This one, 35, what is the relationship between intermolecular forces in a liquid and its vapor pressure? It's simply stated like this: the stronger the intermolecular force, the higher the vapor, or the lower the vapor pressure. Wait a minute. Viscosity increases with the increase. Adhesive forces increase. Okay. E. Okay, I said that wrong earlier. Okay. Vapor pressure decreases with the increase in the intermolecular force because it makes it harder for them to escape. So if you held a plane above the surface of a liquid, less molecules are escaping because they stick to each other more. So the vapor pressure is lower. So that one's inversely proportional. Note, if I didn't upload this already. All right, so this one is simply stated as, which one was it? Okay, what is the relationship between intermolecular forces in a liquid and its vapor pressure? The higher the intermolecular force, the lower the vapor pressure. You guys got me there? You understand that? That's 37, 39. When is the boiling point of a liquid equal to its normal boiling point? And the answer is when the liquid's vapor pressure is equal to the atmospheric pressure. Or another way to say it is when its vapor pressure is equal to the pressure above the liquid. No, normal necessarily means atmospheric pressure. Yeah. If you weren't in atmospheric pressure, then you would have to get the vapor pressure up to whatever the pressure is, whatever it is. But the normal boiling point, you use that word normal boiling point for atmospheric pressure, 1 atmosphere, which is also about 100 kilopascals. I haven't gone over this yet, but I mean to, so I'll include it in the list. Estimate the boiling point of water when the atmospheric pressure is 83.3. So atmospheric pressure is right at 100 kilopascals. But if I go to this figure, I wouldn't have you memorize this. I just haven't gone over this yet. But this tells you, so let's talk about water. So if you have, this dotted line represents 100 kilopascals, maybe it's 101, but this is atmospheric. So this is showing all across here, that's atmospheric pressure. At 83, which would be about here, this problem is saying, estimate the boiling point, the boiling temperature of water, if the pressure is not atmospheric, but it's lower than that, which was about 83. If you eyeball across to about here, down to about here, I don't know, 95. You see that? I would estimate that to be around 95. I will give you this on a test, but I really haven't gone over this, so maybe I shouldn't have listed that one yet. Which one was that? that's 41. 45. Okay, CH4 to NH3 to H2O. CH4 is 45. Yes. We'll look at drawing more. That's it. CH4, H2O, C2H6. Eyes are playing tricks on me. So this is listing what does it say? Boiling temperatures? Same thing. Enthalpy of vaporization. Why is the enthalpy of vaporization higher for this and lowest for this? Think in terms of intermolecular forces. You say size? Size. So none of them have this, none of them have this. It helps to remember that carbon to carbon and carbon to hydrogen are not polar. So you don't get dipoles with carbon to hydrogen and carbon to carbon. Because so many examples are like this. So the difference is based on dispersion. And this one has more dispersion forces simply because it's bigger. And this one has the weakest dispersion forces because it's the smallest. If you wanted the answer in a simple answer, the word would be size. You could also say molecular mass, but I think size is the better answer. This is similar to one I did on water. You've got CO2. So if you had this in front of you, what's the other one? 9.8 kilojoules per mole, like that. CS 28, 9.8, and negative 8.4. .8 and I can't keep a number in my head for 2 seconds. Negative 8.4. So if 9.8 kilojoules per mole is the delta H of vaporization of this, if one of the, assuming one of those is correct, which one of them is it for this? You could go ahead and throw away 9.8 and assume they're probably not going to be exactly the same. But you again have to think in terms of intermolecular forces. They're about the same size, so dispersion will be the same. None of them have hydrogen bonding, so that can't be what it is. If you pull out that periodic table and calculate the electronegativity differences, you'll find that this is polar. You also have that. And this one is just either it's nonpolar or it's a much more weaker pole. Much more weaker electronegativity difference. So the difference is based on strength of the dipoles, or polarity. You follow that? Do you? Which means it's probably A. It's necessarily going to have a lower boiling point or melting point, or a lower delta H of vaporization. That's 47. Okay, convert. We've got time. So this is 51. How much heat is required? 422 grams of water. It's at 23.5 degrees C. It tells you it's liquid. And how do you turn that into? That's just what we call water vapor. Vapor at. I might not have listed it specifically anywhere, but when it comes to degrees C, the scale on the Celsius temperature scale is based on water. That's why it's 0 for water, and then they just chose 100. Well, Mr. Celsius just chose 100. They put 100 tick marks in between the two, wherever the mercury was when the water boiled. He said that'll be 100, and that's how the Celsius scale is defined. You would need for this problem, they don't tell you, but I will give you on a test. Just know when you need it. I mean, I will give you these on a test. Vaporization, I know water is here. 2257 joules per gram. What is it? Can't do the number in my head. 2257. Joules per gram. All right. We're starting in liquid. Oh, we need something else too. It's not just the vaporization unit. We also need this for my semester. I'm going to need vaporization. I'm going to need water 4.184. Specific heat I'm going to do as a C. Specific heat of water. So when you're heating water, and we're also going to need it for steam, I'll say CS, specific heat for water vapor. I think that's in this list. Water vapor, 1.864. All right, so transition point. This is heating water, and this is heating the steam. So what this is saying is, here's ice, water, steam. We're starting at 23.5. We're going to go all the way up here to 100. And then we've got to continue. It's about here, I guess I put it. No, 150 would be up. This might not be to scale. So we're taking a sample from here to there. We've got to go all the way up to here. So we're going to use specific heat of water to calculate 23.5 to 100. And we're going to use specific heat of steam to go from 100 to 150. And then for this transition point, we're going to use this to find out how much heat it takes to boil 422 grams of water. You follow me? So the way this will work is, let's start here. Let's find our delta T first. Final is 100. Initial is 23. 25. Also delta T of water. Delta T of steam is final is 150. Initial is 100. So what do we get here? 77.5. I'm not going to trust it. 100 minus 23.5. 76.5. And then the steam is going to go from 150 to 100. This was probably okay. I don't know what I was thinking. Whatever. This isn't going to be a scale over here. So this is 50. So now that I've got that, let's start at 23. We're going to go for water 4.184 joules to 1 gram to 1 degree C. And then next we want 422 grams. And then our delta T for water, 76.5 degrees C. So I will say that's Q1. Q2, let's do the transition. That's using this. 400, let me write the thing first. 2.257 joules to 1 gram. And then 422 grams. Calculate that out, you'll get Q2. And then the last one, we're going to use 1.864 joules for 1 gram, 1 degree C, 422 grams, and then 50 degrees C is a delta. And then Q1 plus Q2 plus Q3, that's how much energy it takes to take 422 grams of water at 23.5 degrees C to steam at 150 degrees C. Make sense? You followed that, right?
Do you use like the natural law of in this?
No. That whole calculation was a way to estimate these values. Typically, you can just look them up, but this class just throws in a little bit of theoretical thermodynamics for you. The last one on this list I'll just say 53. We can go on. We can end it there. I'll say 53. You guys okay with this so far? So far, that's the types of questions you need to be able to answer on a tax. And I need to get some practice for you in D2L. I just haven't.